So today we start lecture 79 in the helicopter dynamics course, and today I'm going to talk about unsteady aerodynamics. I'm Dr. Anjan Ganguly. Now let us look at some of the sources of unsteadiness as far as the helicopter rotor blade is concerned. So we are very familiar with the pitch motion. So essentially you have an airfoil section and there is some angle at which this section is placed with respect to the velocity coming from the front. Now, what actually happens is that this alpha is a function of time, and in that case, there is the presence of the derivative here. So, essentially, this is going through some kind of vibratory or oscillatory motion, and because of that, you get the unsteadiness, and this primarily comes from pitch. So, it's in the control and torsional response. The second case we look at is plunge, and plunge happens because the airfoil section can move up or down like this, and this motion is given by H dot, and this is known as the plunge motion. For example, think about the blade flap motion. Essentially, the flapping blade is going up and down like this, so it is creating a certain velocity component H dot, and that in turn is going to give you a certain angle, which is also a function of time. So that's another source of unsteadiness. So in fact, the pitch and plunge are the two key sources of unsteadiness in a typical rotor. Besides this, there are some more sources of unsteadiness. For example, you have time varying velocity itself. So we have seen that in forward flight, the velocity is time varying. It is a function of psi, and therefore it is a function of t. So v is a function of t. Secondly, we have taken a look at the lag motion. For example, the lag motion itself is a function of time, therefore zeta dot is going to be present, and so there is unsteadiness in this direction also. Finally, there is the possibility of a gust coming and hitting your airfoil section or your blade. So a gust is essentially something like this. It's a velocity profile in this direction, and when it hits the wing section, it will also create certain unsteady effects which are going to be there. Now, all these unsteady effects will cause certain complications for the flow. They are going to impact the lift, drag, pitching moment, and so on. Now, we are not going to go deep into unsteadiness, but we are going to discuss some of the basic parameters which are used to figure out whether a flow is unsteady or not. And the most important of these parameters is the reduced frequency. So this parameter is essentially used to describe the level of unsteadiness in the flow and whether we should use unsteady aerodynamic modeling or not. So this parameter K is defined as follows. So it's basically the frequency at which the motion is taking place into the chord divided by 2 into the velocity. So here you can clearly see that this is a non-dimensional parameter. For example, radian per second into meters at top, and here you have meter per second. So essentially you have meter per second and top and bottom both, radian being non-dimensional. Now if we look at the presence of no frequency here, that means if this is 0, then you are going to get k is 0, and that is going to be the pure steady flow. But also in case the value of k is very small, for example it's between 0 and 0.05, it's typically known as quasi-steady flow. If the value becomes greater than 0.05, we say that unsteady effects have started to show up, and we say this is unsteady flow. And if k is greater than zero point 0.2, then unsteady effects will dominate, and this is where we need to seriously consider the unsteady impact, and they are going to be quite substantial. Now, we can immediately see that in helicopters, this concept of K or reduced frequency is a little difficult to implement because the velocity V itself is not well defined. Remember, the velocity V is changing throughout the blade span because V is a function of R, because one of the components of V is the rotation speed, omega R. Furthermore, as you go around the rotor disc, V is a function of psi, so that also means that at different points at r and psi along the rotor disk, the sectional velocity is going to be different. So essentially the reduced frequency is going to be different at all parts of the rotor disk, but we make certain approximations to get a value of reduced frequency which we can use to classify some of the modes. So let's, for example, look at the first flap frequency of a rotor, which would be somewhere like 1.05 per rev for an articulated rotor. So if we take the reduced frequency, what we could do is we could take a velocity at a given section. So let's say we take a section like at 0.75 times the blade radius, and we figure out the velocity at that point. So that would be something like 0.75 into rotation speed into blade radius. Now here this would be perfectly correct if our condition is present, so we can certainly assume this. And then on top in the frequency part we have 1.05 into omega, and then we have c by 2. Now for a helicopter, r by c, let's say it's about 10, and in that case we get K75 is 0.07, which is in the unsteady range. Remember that more than 0.05 is unsteady, so we can say for the first flap frequency it's slightly in the unsteady range. So one more thing to realize is that the reduced frequencies will go up as you go inboard of the blade because the sectional velocities will become lower, and that will come out from the formula. Remember that velocity is in the denominator, not in the numerator. Now let's look at the torsion mode. So the torsion mode of a typical blade would have a frequency somewhere between 3 to 4 per rev, and therefore K here would be about zero point 0.2 at the tip. So this is quite unsteady, and therefore we can say that as far as the torsion mode is concerned, the unsteadiness is going to be much more. So again, this just gives you a qualitative understanding of the fact that as far as helicopter blades are concerned, the unsteadiness may depend on the mode you are considering, and certain modes or certain motions are going to be more unsteady than the others. Now, because of the complexity associated with using reduced frequency for helicopter rotor problems, a different parameter is very often used, and this is known as reduced time. So this is defined as follows here. S is 1 by B integral 0 to T V dt, or 2 by C. So this C by 2 is very often used. We saw it being used in K. We are seeing it being used in S also here. And C by 2 is simply B, or it's also known as the semi-chord sometime. So now if we look at it again dimensionally, we see that V dt, this has the unit of distance, and C is also a distance. So both these are in meters, so this is again non-dimensional. So we can think of this reduced time as the distance traveled by the airfoil through the flow in terms of the semi-chords during time interval t. So that's a way to look at it. Now, reduced time is useful to characterize many events occurring in unsteady aerodynamics, such as dynamic stall and blade vortex interactions and so on. And in fact, you can take a look at a lot of literature which is out there in using reduced time in the case of many problems. So we are not going to go into detail into that, but I can tell you that as far as helicopter aerodynamics unsteadiness is concerned, reduced time is much more frequently used than reduced frequency. Now, Theodorson's theory is one of the main theories used as far as the fixed wing problems are concerned. And this theory gives solution of the unsteady loads for a 2D harmonically oscillated airfoil in inviscid incompressible flow and subject to small disturbance. So this theory is based on reduced frequency K, and this is a very fundamental theory. You can find it in many books on unsteady aerodynamics and so on. But this is very much developed for fixed wing, because in fixed wing you can realize that V is very well defined and frequencies are very well defined. especially as far as an airplane is concerned. It always flies at a certain velocity v, which is its general cruise velocity. But we also saw that the reduced frequency is ill-defined for rotorcraft because velocity is a function of both r and psi, and therefore one of the ways to use reduced frequency is for some qualitative work, whether you are trying to figure out the degree of unsteadiness and so on. But helicopter aerodynamics is typically based on reduced time s, and there are a whole bunch of algorithms or methods which have been developed using Duhamel's integral, Jones approximation, and so on. You can find a lot of detail in the book by Gordon Leishman on this subject. So that's somewhere you can go to if you are interested more in the study of how to use reduced time to figure out some of these aerodynamic forces and loads which are acting on an unsteady helicopter rotor blade. So I will end lecture 79 here, and I will see you in a video sometime soon. See you then.